Okay, this will be our last section of notes for trig. But they're dandies, some story problems. So I got 4 examples for you today. Call this 7-5 day 2. We're going to first start with an incline problem. These are probably the easiest ones because they all take on the same triangle. So the way these work is you're going to have some kind of an incline, a hill, a ramp, something. So the hill or ramp has an angle, and then you're going to have some kind of a weight on that incline. And then there's forces acting here. We've got gravity that's going to pull straight down. And then you've got the friction on the hill. Those are your 2 acting forces. And when you slide this friction force down to the arrowhead here, I don't know why, there's some physics behind it, but when you draw in the resultant will always make a right angle here. So this is gravity pulling the weight. That's equivalent to the weight. That's what gravity's pulling. This is they call it the force needed to keep it on the hill. I call it the friction. I don't know if I'm right on that either, but we'll go with it. So this horizontal one, I call it friction, but it's the force needed to keep it on the hill, to stop it from sliding back. You need that much friction. Force needed to keep W on the incline. Doesn't slide back. So gravity pulling the weight, equivalent to the weight, friction, and then resultant. All right, so here we go. Number 1. Find the force needed to keep a 3,200 pound car on a 15-degree incline. So here we go. Picture first, 15-degree incline. Oh, forgot a crucial point here. Back up here. This triangle with the hill, there's a right angle here. This triangle somehow is similar to this triangle. So the angle of the incline is the angle right here at the top of this right triangle. Those will always be the same. That's what makes these problems pretty easy. You always have this right angle. You always have these 2 angles the same. So here's our car. And then here's gravity, 3,200 pounds. So gravity pulls down, 3,200 pounds. It's asking for how much force is needed to keep it on the hill. That's what we're looking for. We'll slide that down here. We'll call it F. Draw in our resultant. That makes a right angle. And we can transfer the 15 degrees into the top of our triangle. Now, because it's a nice right triangle, we can just do SOHCAHTOA. Oops, I'm not on the... Hold on, sorry about that. It's hard when the video's behind me. So there's our picture. Let you get caught up on that. Sorry about drawing off the screen. But here's a nice right triangle. We're going to stand here at the angle that we know, the 15 degrees. We are looking for the opposite, and we know the hypotenuse. So this is just a sine problem. So sine of 15. Opposite is the force I'm looking for over the hypotenuse, 3,200. You could have done law of sines here too and done proportions with the 90 and the 3,200 and the, yeah, you could have done that way too. Either way, got lots of ways now. So cross products. force gets multiplied by 1. Sine of 15 times 3,200. Sine 15 times 3,200. 828 pounds of force. Oh, it looks like 2 sig figs, 830 pounds of force. Here's a tough one, and you're going to have one just like it, but I think you can go look back at this one and repeat the process. Okay, whoops, right here. Number 2. Okay, we've got 3 forces acting on a point. So see this as 3 ropes pulling. And they are all in equilibrium. That means nothing's moving. It's like a tug of war with 3 ropes and everybody's staying still. Nobody's winning this tug of war. Yet everybody's working hard. And we'll see what has to happen here to make that situation occur. So can you find the angles between the 3 forces? So force 1 is pulling with 980 pounds of force. Force 2, 760 pounds of force. Force 3, 1,220 pounds of force. So, remember, all 3 are pulling, but nothing's moving. So if you think about it, logically, with 3 people pulling and everything staying the same, that would mean to me that these 2 weaker ones are counterbalancing the strongest one. It's taking these 2 people, the resultant of these 2, to pull against this one. So think of this one as the equilibrium force for the resultant of these 2. So if I do that, I'll go with the 980, the 760, shorter, 760. So those 2 are tail to tail. If I am to draw their resultant by making a parallelogram, $760, $980, that resultant is the counterbalance to this 1220. That means my resultant is also 1220. So our goal said find the angles between the 3 ropes. So we want to find this angle, and this angle. So 3 different angles we want to find. So let's find, I think it would be best if we found each of these individually. Because if we found each of them, we could add them together to get this angle between them. And then remember, this is a straight line here. So angle 1 and this angle out here would make 180, and angle 2 with this angle down here would make 180. So if I knew these 2, I would be able to get all 3 angles. So that's just a lot of law of cosines, 2 of them, for side, side, side. So I'll call this angle A and this one angle B. Change those out. So if you remember how law of cosines works, cosine of A, so you're standing on A, you have to have the side across from it squared first. That's crucial. So that'll be 980 squared. Subtract the 760 squared. subtract the 1220 squared, divide by -2, times the 2 subtracted, 760, and the 1220. So you will do them. I'm not going to take the time to actually show you all the typing in. Hopefully you can do all of that. Use parentheses. Inverse cosine this. And I've already done the work. This one comes out 39, let's see by the 7, 53 degrees. Now to do B, same thing. So I need the side across from it squared first. That's the 760. So you can see we're going to get a different answer. 760 squared, then subtract the 980 squared, subtract the 1220 squared, divide by -2, multiplied by the 980, multiplied by the 1220. And again, parentheses, parentheses, inverse cosine. Angle B came out 39 degrees. So if we go back to the picture now, you should be able to answer the question of find the angle between the 3 original ropes before we do all the calculations. So A was 53, B was 39. So the angle between, let's see, this was force 2, force 1, force 3. Let's see, 53 plus 39. First answer, 92 degrees. Then the angle out here will be 180 minus 39. That'll be 141. And then 180 subtract 53. 137. Now I didn't do that right. Double check those. 27. I knew that one wasn't right. 127. Okay. So you will have one like that. Just look back. Hopefully you can follow. And that'll make sense. Let's see. I think I'm going to go with 2 more. Number 3. Okay. It's all about the picture. You have to be able to draw a good picture. We've got a crate. Oops. A crate. That's terrible. Crate supported by 2 ropes. So it's suspended from, I don't know, a rafter or something. So it's up in the air. I don't know who would string this up this way, but one rope pulls due west. One rope, the other rope, at an angle of 46.3 degrees. And the second rope has 89.6 pounds of force on it. Can you find the weight of the crate? Okay, so here's our picture. Not a very easy one to do on your own without seeing one of these. So we've got a crate that has some weight to it. It's being suspended up in the air with 2 ropes. One rope is pulling due west. Doesn't tell us how much weight's on it. The other one is making an angle of 46.3 degrees with, I didn't say it very well, but with the crate. So think about it. It would be impossible to have that both ropes pulling this way. It would just swing over. So that means the 46.3 degrees is right here. And this one has 89.6 pounds of force on it. All right, so remember, these two ropes are supporting the weight of the crate. And remember, the weight of the crate is being pulled now by gravity. So these two ropes are counterbalancing that. So that means when I slide these over, make my parallelogram, see, that's a little long for my picture here, I can see, and so was that one. My counterbalance has to be, remember, just the total opposite of this one, so it's got to be due north. So my resultant is right here. So my resultant and my equilibrium, I should have shortened that up a bit. Oh, let's shorten it up. There. And this was a little long, because it's got to match that one. We've got a right angle here. Because that one was pulling due west, and this one's supporting it due north, we got a right angle here. And then we can move inside the triangle. Oh, we could alternate interior up here, 46.3 up here. Alternate interior, or we could subtract from 90 and go here. 43.7. There's all kinds of ways to get inside of the triangle. And the goal was to find the weight of the crate, which is going to be equal to the resultant. The resultant and the weight of the crate are going to be the same thing. So now I can just do, let's see, if I stand here, this would be adjacent, and I've got the hypotenuse. So I will go with a cosine. Cosine of 43.7. If it wasn't a right triangle, I would probably have had to use a lot of sines, but it is a right triangle, so I just always go back to SOHCAHTOA stuff. Adjacent over hypotenuse. A little cross product. Cosine 43.7 times 89.6. Let's see, we got 64.8 with 3 sig figs. So the crate weighed almost 65 pounds. Okay, the last trig example of the year. Let's throw some bearings at you. How much time? Ooh, I got 12 minutes. It won't take that long. Okay, number 4. Let's see. So we are sailing from point A. So from point A, we're going to sail 18.5 kilometers on a 189 degree bearing. Remember, bearings are from due north clockwise. Then we're going to turn and sail 47.8 kilometers on a 317 degree bearing. Can you find the distance from A after the second leg? So find distance from point A. All right, draw yourself a nice big picture. So we're going to start with point A. So we're going to sail 18.5 on a bearing of 189. I like reference lines. Reference lines for bearings are north. So start with the due north line. Put your pen on that dotted line. Turn clockwise 189 degrees. So that's just past due south. 90. 180 is due south, and then another 9 degrees. So, and label everything 189 degrees. And that's 18.5 in length. Now from here, now we're here, now we're going to turn. So you need a new reference point, and we need a new reference line. So a new bearing, 317 degrees. So I need another north line. Put your pen on that dotted line. 317. That's 90, 180, 270, plus some more to get to 317. And 47.8. Oh, that's really long. There. Compared to my 18.5. So this is 317. Okay, this is 47.8. The question is, how far am I right now from point A? Okay, what we need to do is find this angle, and you can usually find each side of this angle. Obviously, we can find this part by finishing off the 360. So if I go 360 minus 317, this side of it's 43 degrees. And remember these before? This side of it can be found with alternate interior angles by extending this and extending this. So remember, it was 180 up to this line, and we went 189. So this angle right here is 9 degrees. So if I alternate interior it, the 9 comes in here. So this angle in my big triangle now is 52 degrees. And now I've got a nice SAS side angle side, and I can find that missing side with law of cosines. So that missing side squared equals the two known sides squared and added. And then we subtract 2 multiplied by each of those. 47.8, and then multiply by the cosine of the angle between them, 52. And remember, that will be x squared, and then you take the square root. Not going to take the time for the calculator work, and you should be able to get 39.2 kilometers. And that's it for trig.